went through all the quizzes and homework problems and without summarize. So when you see this sort of problem, what should you do? You know, things like this. So the first one, I'll just do a very quick review on this. Okay, so there's one student got 100 and a couple of maybe one or two like in the 90s, and then spread through all the ranges from like 60s to 80s. So average score is probably 70 something, 75 or so. I didn't calculate it, but estimated, and usually that's very accurate. 73, let's say. This one, surprisingly, 80% of you guys didn't model this little gate, and I don't understand why is that. You model this one, put a module, and you directly put this one in the top. Why is that? Right? This should be another module, right? And in order to connect all the three modules, you need a top. And that top is a system top. It's not a simulation top. Don't get confused. The top is still a module. Simulation, the simulation top. But the top for these three things, the three gates, is a chip. You don't need any simulation files in it, simulation stimuli or signals in it. It's just the top module. It's simply just a chip. So in that case, you can imagine, hey, I have three wires, and the middle wire is shorted to the port. So in your top system module, you don't really need a second wire or the third wire here. So you only need two intermediate wires for the internal signal connections, and all the rest are just ports. So in your top system, you need two wires. So why not three wires? Because the third wire is shorted to the port, so you don't need this wire. You know what I'm saying? So if you look at, remember we have done this for many times, right? So when you are putting all the sub-modules into a top module, if they're not directly interfacing with the ports, you just have to create an intermediate wire in the middle, like a floating wire, so you can indirectly short the two ports to the single wire and make the connection, right, in your top. But now, since we have 1, 2, and this one is just a port, so we don't need an individual wire in the top. So if you look at the code here, okay, it's hard to see, that's why I printed it out for you guys. So where are these two wires? Oh, this top is the simulation, right?
Yeah.
And this is the system top. So for this problem, you need 1, 2, 3 sub-modules and one system top to put all the three sub-modules into a single chip. So you need the two wires, A wire and C wire. So these are the two wires over here. It's A wire and C wire. All right? And then just make connections. So for all the other sub-modules, to make it simple, just name it as ABY. So all of them are ABY, ABCY, okay? Because all the sub-modules ports are not visible to the top, to the upper level module. Like what you did in VSI, right? It's the same thing. When you have all these little sub-modules ports, they are not visible to the outside. Whenever you make the connections, that name of the port, the name usually, for example, you had A and B or something like that, right? Whenever you make the connection in the upper level module, eventually that name will disappear. So you can name it whatever else you want. So you can right-click the arc and rename it. Same principle over here. Okay. So we just do the same for all these sub-modules, so we don't have to change it. And for the system, you look at the name of the ports and give wires, make the connection to the ports to ports, and ports to wires. This is a really standard way of modeling all these combinational logic blocks. I think you guys should be able to do this really easily and quickly. So if you still cannot do it, I think probably there's a chance that you'll fail this again in another quiz or test in the future. Okay? Look at the top. So top, because there's nothing to be connected to the VGA, it's a simulation. So no ports. You don't need the ports. No ports is needed. And instead, you have all the internal registers or flip-flops are holding values to provide stimuli to the system. Okay? You can see A, B, C's are zeros as initial values are given, so that's why they have to be register type. And wire is the Q is the output, which is the final output over here as a Q. I assign a wire to it because I want to probe it. You just need a single wire, like when you put a wire, connect a wire to the clip of the multimeter, right? And then you probe it. So it's just a single wire to probe it. You don't need a latch. There's no reason to put a clock to control it, right? Just probe it. And I place this system into the top, the simulation, and I make the connections from the ports of the system to the stimuli, right? And the probe. So initial statement only execute for once, but the thing is you can add a repeat statement here to repeat it for multiple times. So a few problems I found. First, a lot of people don't know how to use this one, the repeat statement. You guys just didn't use it. Okay, it's really simple, way better than the for loop. And a lot of you guys don't know how to use this one, concatenation and adding, incrementing by one. See how simple this is. You have to list all these stimuli in a long list. It's directly adding to it and add a repeat statement in front of it. Another problem I found was you see a constant value of the time delay after the time delay without having changes. It's because you have a semicolon here right after the time delay, which is wrong. And eventually it's not making any changes. So the goal of this one is making the whole thing here in this line one statement. So the point is, right after this time delay, it is able to add a point to it. And this is extension to the previous value. You know what I mean? So this one is the delay of the previous value. So for example, after this addition, the value gets changed. So this statement is only, because there's no time delay for this single statement, so it's only making a change to the final output. So eventually it's just a point, just one point. Which is fine, because next time when it repeats, it's gonna add this 5 nanosecond time delay to extend that point and to make another change. So these are just the points, keep in mind, these are just points. And that's a place where you extend it. You extend the point. So you don't need a semicolon here. You want to make the whole thing one statement, just one line. Okay, so no semicolon right after time delay. For the second one is a subsystem. The parity checking, even though I didn't say it's a parity checking system, but it is a parity checking system. So you can see it has a B output, and it's holding values, and also it changes, right? It changes. It's holding either 101 or 01. So in that case, we want this one to be a register type, and so we can assign the initial value to it before we do anything. And you can see there's no clock, right? If you add a clock, I probably didn't take any points off. If you just look at the module, we don't care about the input and output. It's basically just a 6-bit input and 2-bit output, no other ports. In the future, if you add more ports to it, I'm going to take points off. Shouldn't be any other ports. Input, output, done. Okay? So in your code, when you model it, see, input, output, no other ports. No other ports. And then when I start typing, so that's how I did it. When I start typing, I find out I need to look at a intermediate output, which is I can assign it to Q. to check the result of bitwise XOR, because when I'm looking at even number or odd number of ones of A in A, I need to do an XOR logic for every single bit. It's a bitwise XOR. So there will be an intermediate wire to hold that value, because all the XOR logic is just a combinational logic. So I can directly XOR them and assign to a wire name as Q. So we have done this for so many times, right? So assign something to something is a very standard data flow modeling method. Okay, so Q will be available, it's holding something, and Q can be put into the if statement. But however, because Q is changing, so you have to place it into a behavioral modeling block like this. I found this from when I was coding in Vivado. Nobody tells me that. When I put it outside, if I don't have the always block, I put the if statement outside, it's giving me errors, and it tells me you have to put in the always statement. So I just did it. That's for whoever designed the syntax of Verilog, right? Just follow. So I placed it in here, and I find out, hey, I only need to update the output whenever A changes. If A doesn't change, there's no reason to change the output, right? Because even though it's a combinational logic, it's still depending on the inputs. If inputs changes, I update the output, which makes perfect sense. So in that case, A will be in a sensitive list or on the sensitive list. That is why I have always add A. So when A changes, then everything gets updated. Okay, that's how the sensitivity list works. So if Q is 1, right? So when A changes, I'm going to check Q. If Q is 1, I start, I don't even need a begin end because there's only one line, right? So if Q is 1, which means it's an odd number of ones in there, so I'm giving this to B. Otherwise, I'm giving this 1, 0 to B. And that's it. That's the whole entire logic of the circuit. Done. And then you need the top. So to verify the different combinations of the inputs. So there's no ports because it's just internal signals from the register. And A's, why I need a register type of A's? Because A's are holding values, right? A's are holding values. I need to give A values, and they're holding them. And I also need an initial value for A over here. So initial beginning, I'm giving an initial value to A. So A is holding an initial value. So it has to be a D flip-flop. That's why it's a register. And I'm just probing B. And start giving stimuli to it. So give a 0 to A at the very beginning and then repeat it for 8 times. You can do more times if you want. But definitely this will show you a lot of different combinations already. Right, so just correct myself. So seems like we don't need a register type for B. No, we do, because here is already register. It's already inside submodule, so we don't need a register again for the top. So we just probed the output of the D flip-flop. All right. Yeah, don't be afraid of making mistakes. At the very beginning, just start typing and typing out whatever you have in your mind, and then fix it. You just have to make it happen first, and then gradually fix it. Okay. So for the third one, the example is given. Trying to make it easier. It doesn't seem to be easy enough. I realized that letting you guys type up that decoder's 7-segment displays code in there is a little bit too much for the exam. So I should have given that to you guys. So that's my fault. And what are the J's here? Anyway, sorry about that. Just saw this. So this is one of the quizzes that I gave to you guys before, right? And the solutions were given as well. It's basically just counting. It's counting. And if you see this count max over here is 100 million. So it's counting every 1 second. So it's directly giving the count to LED, or it's incrementing LED. But in order to connect the counts directly to the sag, you will need a decoder. You will need a decoder. And since we don't use this LED anymore, we're not displaying anything on the LED anymore. So eventually, you can change this one to sag, right? Just change one to sag. And that's a 620 sag instead of LED. Or if you prefer digit, oh sorry, shouldn't be 620, should be 320 digit. The reason for that is we only need 0 to 9, so totally 10 different combinations of outputs, and 4 bits of digit will give you 16 options, so it's good enough. So we only need the 4 bits. So in that case, if you look at all the module structure, so if I'm doing that, I'm gonna draw the blocks first and draw the inputs and outputs, so you know, at least you know how to program the first line, right? So for the first one, that's a counter module. You need a clock, okay, and there will be a switch, and there's a digit, 4 bits. So for the decoder as well, you need the 4 bits to receive the digit. To receive the digit and use a case statement. So case digit, case parenthesis digit, 0 to 9 to show different sags. Okay, and the 7-segment display module on the IPGA requires AN, which is a 4-bit register. Since we're only using the one on the right hand side, so you want to give 1110 to it as a constant. So in that case, it's a constant, it's not changing, and you can just directly use a. You don't need a register for this. It's a constant. Just directly throw these values to it. You can imagine it's gonna pull these 3 pins up to VDD and pull this down to ground. These are just wires. Just pull them down and pull up and pull down. So they're not changing. You don't need anything in the middle to change it. But for whenever you have to change it, like the ones we use for the lab, and we are even shifting it and doing all these kind of operations, you need a register, intermediate register for this one. And for the sag, it just directly assign to the output, right? So you need a wires for these guys, and you need a clock for this guy as well. So the clock is to synchronize everything and update all the values in it. It just always add the clock, update everything, right? So synchronize all the changes. Anything else do you need? That's pretty much everything, right? So if you look at the solution, see, I didn't change anything except this one. So instead of directly throwing all the numbers to the LEDs and display on the LEDs a binary number, I'm creating a digit over here, a digit. So the 4-bit digit are being sent to the decoder, right? So we don't have to worry about that for now. Just short it to the decoder. And for the decoder, it's super simple. And that's the code for the 7-segment display for the patterns. And clock, digit, input, output, AN, output register sag. So the register sag is because it's assigning values to it and it's changing. And for the top, you can see we need a wire in the middle because the digit here is a wire, intermediate wire in the middle. So we need a wire. That's why I put a wire here, 4-bit wire. And then instantiate the 2 modules. You can see the top is super simple. because it's the IPGA top. So it's really simple because all the signal or stimuli are given by the either internal clock or switch, and output are directly shorted to the patterns. The top is really simple. I mean, if you couldn't get this done, but at least the top should be done easily, right? Any questions on the midterm exam? By far. Good so far? Yeah? Well, no worries, it's just need more practice. Okay, just imagine if this is a NVIDIA interview. What's gonna happen? It's very likely, right? So the NVIDIA interview in UCLA have a long line for everyone to take a quiz. Just write down Verilog on the paper. Okay. It could be very similar to these ones. Just model a counter, or model a display, model a whatever state machine. So we'll work on that in the following weeks. Okay. And next, let's look into the in-class exercise. So I'm picking up 2 questions from this for the quiz on Thursday. See how many of them you can answer immediately now. Doing the first one. Then the second one. The third one. First one. If I make it close book, close notes now. Oh, sorry. I was I turned on something over here. Right. So let's look at this one. So this is a schematic I put on the website as well. Just really quick calculation, so you guys know the internal structure of all the wires over here. So superposition. If it's a 5 volts logic, possibly you are giving 5 volts or logic 1 to either of them. If VGA G, that's a green channel. From 3 to 0. It's 0011. Okay, so the analog output will be, you can calculate it. And the way to do that is, if the people are in VLSI, probably this is easier for them, but if you look at this one, you do superposition, right? Superposition. And these are both grounds, and you don't need to do anything, but for these ones, you analyze one each time. So for this one, C5, let's say VGA green 0 only, right? So in that case, this is the common output, and these are all grounded, and 5 volts here. 4K, 2K, 1K, 510. So we're getting V out 1. How do we calculate V out 2, which is 5 volts here? Okay, calculate this based on this voltage only, and add, so VL analog equals VL1 added to VL2, okay? The second problem, given that it's a 100 by 100 total pixels, so this includes the both visible and also the porches, back front porches. And also the sync signal. includes all of the pixel times. So keep in mind, it's not just the visible pixel, it includes the pixel times. Just the pixel times. It's just waiting for something to happen, right? It's a old, very old protocol, has to accommodate the traditional monitors, but probably not the monitor we have in the computer lab. But anyway, just have to follow the protocol over here. So how to do this calculation? I know this is really simple, but sometimes it confuses people. 25 megahertz is a pixel rate. Okay? So 25 megahertz means what? Mm-hmm. So that's the pixel rate, okay? So how many pixels do you have? So, yeah, 10,000, and this is asking for screen refresh rate. Is a unit frequency or it's hertz, right? So the rate is hertz. So you have 10,000 pixels, and you have 25 million pixels per second. So that's why you want to do a division like this, because if you do a division like this, pixels are getting canceled and second will be flipped to the top. So eventually you are getting what? How long it takes to refresh the whole screen just by one frame, right? And then you'll do 1 over it will give you hertz. Make sense? Okay. How many bits are used for each color channel in the Verilog example on the tutorial? Yes.
3 for red, 3 for blue, and 2 for green.
Mm-hmm. Let's take a look. That's pretty, I think that's right. Take a look. I talked about this the first class I introduced VGA, but just in case, it's good to repeat it a little bit. RGB, how many bits for R? 0 to 2 is 3 bits. How many bits for green? 3 to 5 is 3 bits. And for blue, it's only 2 bits. There are only 2 bits to resolve the blue color. On or off. So if you look at the, and unfortunately our basic 3 board is a blue color board, and that is why it looks so ugly on your monitor. It shows a greenish color. And so another question here is asking, since we are using 8 bits, right, it doesn't mean that there are only 8 bits available. So how many bits are available for each color channel in the constraint file? 4 bits, and you can also tell from here, right? See, 1, 2, 3, 4. But we're only using the lower 2 bits. Only using the lower 2 bits. And lower 3 bits for R and G, and lower 2 bits for blue. As a constraint file. VGA red 0, 1, 2, 3. Okay, 4 bits for each channel. If you want to have a better resolution, better color, you can use all the 4 bits. Use all the 4 bits. And then move on to the LCD modules. But I think we should talk about the lab for the VGA first. Let's take a look at it really quick. The lab. Oh, so for the code for the VGA, I was looking at the assignments and not a lot of you guys have turned it in. Seems like you guys are having a hard time. And that's why I delayed the, is that lab 5 or lab 6 for one more day for you guys? Lab 5?
Yeah.
Still working on it, right?
So
Yeah, that was like 8 or 9 p.m. yesterday. Only 5 turned it in. So like, I know a lot of people are anxious about it during the night, so I just delayed it. So for VGA is due tomorrow.
yeah.
It's a lot of pressure, right? Haven't got this done yet. There's another one waiting for you tomorrow. So this is given, right? So if you plug in and run it to the board, you should immediately get a picture, get a basically 3 boards picture on the monitor. Okay, this should be simple. And the way that works is it's just scanning through all the edge and vertical, the horizontal and vertical counts, and see if it's reaching the limit. If reaching the limit, then switch to another the second row, the row next to it, right? And keep doing this. And there's an enable flag over here. So whenever it satisfies all the range limits, so which means it's within that range of the visible area, then you enable it. Okay, so you have a flag. See, all these ones are turning on all the flag. So all these previous if statements are just playing with the enable flag. Okay, enable flag. And because this is not a C program, right? Like all the instruction pointers are taking instructions one by one. This is just hardware. When you are programming hardwires, everything will be implemented at the same time. And it's being synchronized by the clock. So when clock arrives, it's going to update all the if statements without following a certain order, right? So that whenever the enable is on, so for all these first 2 if statements, they are handling all these limits, and eventually it turn on enable, and this part of the if statement will detect that change to the enable flag, and then throw the colors to the ports. So this is pretty much independent to all the other ones. That doesn't have to follow these ones, right? It's just checking when the enable is 1, it's going to start doing this. And you can tell that the pixel data are being assigned to the ports, the 3 color channels. And if it's not enabled, you should see a black monitor. That's why I put 0 all zeros to it. You should see a black. And that's the end of it. Nothing else. You can see these ones are just trying to give a sync signal. And that sync signal is being received by the VGA controller within the monitor. So it's going to see the sync signal and start assign pixels to the next row or column. So these 2 are very standard. You never need to change this at all. So the bottom 2 if statements are not changing at all. So these are all the counts within that syncs range, which is over here within this range. Okay, then just to give a sync signal. That's it. Very simple. So I think for this tutorial of VGA, the lecture, is very straightforward. But I think the next, how many tasks are there? 3. Oh, 3 tasks. I'll show a solid color on it, right? This should be really simple because it's just counting to a certain number and then switch the all the values for the different color channels, right? You can see here's the picture, right? So for the lab today, so first is drawing a line, a green line in the middle, not in the middle, on the left hand side of the monitor. Draw a green line. Let's take a look at, so the code for the first task is given. I post it. So you can have something to start with, right? So you can see it's just a very standard VGA controller, and 90% of the code is not changed. Until you see here, the range. That's the only thing I changed. And tell me if that makes sense. Again, all the if statements are independent. They're in parallel. Okay? When it's do the scanning, and it's within that visible range, enable will be 1. Enable will be 1. But however, what kind of color you are assigning to the color channels depending on the range of the pixels, of the location of the pixels. So you can add another independent or parallel if statement to limit the edge count. Whenever the edge count falls into that range, depending on the width of the green color, the green line. So I'm putting 4 pixels in it. No, 4 pixel times in it. Because they are totally 640, right? 640. So I'm putting 4 in it. So it's 4 out of 640. So you can calculate the ratio of the width. And within that range, when edge count counts to that range, and remember this is running in parallel, okay? So I'm giving a green color to it. That's a green color to it. So the green channel is full. It's F. All of them are 1s, and for the rest of the other 2 channels are 0s, right? And else should be all 1s because it's a white background. And that's the only thing I added to it. Okay. So the one after it, next to it, is adding another bar in here, and code is not given. So for the green line, you don't have to limit the vertical locations because it's going through all the vertical pixels. For this one, you have to limit the range of the vertical counts as well. So it will be a few AND statements, right? So a few different conditions in the if statement. So it's going to be like edge count within this range and the vertical, the V count within that range. And eventually we'll draw another bar in here. So here's a condition in the if statement. Has to satisfy all these conditions in order to place that red bar over there, right? You can see 4, 1, 2, 3, 4 to limit that range of the red bar. And definitely the red color give a F to R, and all the rest are 0s. Okay. For the third one, it's asking you to move that red bar to the right slowly. You can move it faster in order to make it visible, but you can tell it's moving. It's moving. Yeah, how do we move it?
I guess by just cycling through the boundaries.
Yes, yeah. So you increment your edge count limits. So the edge count limits are not constants anymore, right? So you're incrementing your edge counts or limits. And then use a counter to count to a point to update it. So you can change the count max to change the speed of the movement, right? It shouldn't be a lot of changes to it. And the last one, moving the bar faster, a little bit faster, and bounce it back whenever it hit the right boundary here, and the left. It's bouncing back and forth. It's like a game. So you can imagine in the future you can design a game out of it, right? Just based on all the pixel locations. So the what's the challenge here? Think about it. What you are gonna do?
Well, you have to.
So compared to the last one, what's the difference? The last one was able to move, right? So this is just moving faster. So that shouldn't be a challenge because it just simply changed the count max. However, the major difference is it's able to bounce back. So how do you know it should bounce back?
It's like you have to know what the boundaries of the screen are.
Yeah, so whenever the location of the pixels arrives here, right? So it's going to be an if statement if whatever the left or the right locations equals the locations here, then you want to start decrement your locations or the pixel counts instead of increment it, right? Okay, I think this is a reasonable 1 week lab. And let's move on to the LCD ones, which will be the next week's lab. Because there are 3 problems on it, really simple. I won't be able to cover everything. It's a little bit too overwhelming for today. I'm going to introduce the LCD really quick, and then I'll let you guys work on your assignments. Okay. I'll give the time to you guys. So we have been using the LCD modules for the Arduinos a lot. Okay, so this guy, and we never care about the bottom level logic of it because everything has been put in the library. So this time you guys are going to program the controller yourself. And you can see there are several GPIO pins, which are general purpose IOs. And we're going to use the JB ports for, JA ports for the data ports. Let's see this guy. It has D0 to D7 and 8 bits of data. And enable read or write. We rarely use read, since we usually just write to the monitor. We don't read from it, right? We usually don't read from it. I've never read from it. So we are writing to the monitor to display something to the monitor, right? But definitely you can control it, either reading or writing. So it's just a one pane, 1 or 0. RS is a register selection. So it's either writing instructions or writing data to it. So because it allows you to do a lot of setups. For example, the resolution of each digit of each number here. You can set it up. The cursor's moving. How do you want to move the cursor? You want to blink the cursor? You want to don't show anything on for the cursor? You can also set it up. And also 1-line display or 2-line display. You can see you are able to display 2 lines. It's a 16:2 display module. But if you don't want to display anything on the second line, you can set it up as just 1-line display. So in that case, you need to write an instruction to it first before you write the data to it. And there's only one parallel data channel, 8 bits. So this one is being used as instruction and data at the same time. Contrast, you can change it using a potentiometer. VCC has to be 4.5 volts at least. So your basic strip board is 3.3 volts. So you'll need an external power supply. Ground is common ground. Just 0 volts, common ground. Short everything to this common ground, keep in mind. But for VCC, you need external power supply. And which one did we use? We use the Arduino little module here. This guy. So it has a 5 volts and 3.3 volts output, and you plug this into the adapter on the wall, and it's able to convert. So the little plug, the little adapter will convert that AC to 9 volts, DC, and 9 volts DC will be regulated by the regulator on board, eventually giving you 5 volts. So the 5 volts is supplying power to this module. But keep in mind, including the IPGA and this power module and this guy, then you have one common ground everywhere. So a few things you need to know, in order to complete the in-class exercise. Data sheet. You open this up, you have a headache. Okay. Instruction set. You guys are like, seriously, we need to have instructions for this super simple LCD module? You can see all these setups. You can change all the settings. Right? So the thing is, in our, if you look at the code, see here, this is available from the textbook as is given. Okay, so it's writing initial, so it's trying to initialize the LCD display. It's giving 1, 2, 3, 4 different instructions, and they all share the same data line, D0 to D7. And there's no address. There's no address. The only thing you can control is the RS, pin, which is a pin on the module here, is the RS pin. And if RS is 0, see here, RS means register selection or selector. If RS is 0, you are selecting what? So when you pull RS down to ground, it's a physical pin of the module, right? If RS is low, you are treating D0 to D7 as instruction, not data. So you are trying to send a instruction, which is a setting command, to the module to do either like resolution or movement of the cursor and all different kind of settings. That's the only thing you can control. And there's no address for all different registers. So my question is, how do you know which one controls which? It's directly writing 4 different instructions to it, and every single one do a different thing. You see the first one is setting a 1-line display, and every single unit is showing a 5x7 dots, which means 5x7 dots means this little display have 5x7 dots to resolve that little unit, display unit or symbol or number, whatever you want to display in there. And remember, it's 16 by 2, and 5 by 7. There are you can see the dots here, right? You can see the dots. See the dots? And I was counting this. Where can I find you can see here, right? From the horizontally, 1, 2, 3, 4, 5. Okay. Vertically, 1, 2, 3, 4, 5, 6, 7. It's not 8. It's a typo in the textbook. It should be 7, not 8. Just keep in mind. I directly make a snapshot from the code from the textbook. So it should be 5x7, not 5x8. But it's not changing too much. Just let you guys know. It doesn't matter. So the first one set it up as a 1-line display. So you are not displaying anything on the second line because it's 16 by 2, right? It's 2 lines. And every single display unit has 5x7 dots to resolve that character. And so that's the first command doing this. And second command, clear the display, do nothing, okay, clear it. And the third one, increment the cursor. So move the cursor to the right, or it can shift it to the right, shift to the left, depending on the command over here, the code you give to it. And the fourth one is display the cursor on cursor blinking. So the cursors keep blinking, so you'll know which one, which character will display the next character after it. You don't need to blink it, but it's just let you know you can blink the cursor if you want. And then you put up to 1 after that, after you are done, right? So you'll be ready to send data instead of instructions to it. So my question is, how do you know which one is doing what? I mean, can I swap them? What if I do this one first and do this one in the second?
That should be fine. Because it's just the bits, right?
Yeah, just the bits.
Yeah, so you can do them in any order, right?
Yes.
Yeah.
And why it knows that this line setup thing is not doing something for this mode. For example, this is clearing, right? If I have like 02, for example, it's displaying something or not clearing. Why it knows this one is setting up the line mode, but not doing something here. Even though there's no such a code like 02 to do something else. But how it knows?
Is the change in the RS bit?
The RS is always 0. RS is always 0 because right now you are doing the instruction. You are not sending data to it. Let's take a look at this one, see if you can find some clue here. Take a look. So these are all the commands, and keep in mind it's really simple. There's no address. Doesn't like the other modules you have used before, right? You are sending a certain command to a certain address to do something, right? But this one doesn't have an address. How do you know which one? So for example, if I put this 30 here, right? So how do you know that this one is doing the line and pattern setup instead of something else? So how do I know it is doing the function setup? Function set. The first one is the function set. Oh, is the first one function set? Yes, the first one is the function. How did I know that?
Is it because the fifth bit is enabled?
Huh?
So is it certain bits, if certain bits are enabled and certain bits are not enabled?
Yeah. Which one?
I guess for specifically that one would be the fifth bit.
You know what I'm talking about?
The function set?
Yeah.
Yeah.
How do I know the first line is doing the function set, but not doing something else? Take a look at the pattern here.
So, yeah, so. Yeah. Well, yeah, so it's doing it based off which bits are enabled which ones aren't, and specifically it's doing like a step pattern. So it'd be like the fifth bit enables all of the function sets, and then you can change the other 4 bits below it.
Yeah, that's right. So did you see this bit here?
Yeah.
It's always having one bit with the one bit here as a 1. You can see 1, 1, 1, 1, 1, 1. Okay, and keep going. 1, 1, 1, 1. Okay, so that means if you have a 0, 1 here, if you look at this one, if you put a 1 here, 0, 1, 1, 0, 0, 1, 1, it's going to be a 0, 3. No, 3. So this number, this 4 bits, 0, 0, 1, 1 becomes a 3. And that's the only mode it can be if you have a 3 here, because all the other ones are having zeros at bit 5. Okay, so it knows that it has to be this one, right? And you just make all the other settings here. Don't let 3 happens over here, guys. If you have a certain number, it just have to be that mode. It's like a decoder, right? So I think you are able to answer question 5 now. And for question 6, because we're not reading from it, Are we reading from it? No, we are not. We don't need to read from the LCD module, so we're only writing to it. So in that case, you need to give a 1 or 0 to RW. It's a physical pin. Okay, it's gonna be a 0. Okay, since we don't need to change it, so in that case, you can directly just ground it. So when you are making the connections, just directly ground RW. We'll be fine. You're always writing to it. And there's one thing you need to know, even though the timing diagram looks very complicated, but however, because this is always 0, it's always put down, so you don't really need that TAS, which is right whenever if you previously you were reading from it, right, and then you put it down to write, then you need a TAS, right? TAS is a time here which is minimum 100 nanoseconds to change the mode from reading to writing, right? However, we're not reading from it at all, so it's been sitting there for like super long. So right, like few seconds at least. So this really doesn't matter. You don't have to worry about this. You just ground it. It's going to be always 0. You don't have to worry about that. So for RS, you do need to change it from 0 to 1, because when RS is 0, you are sending instruction, right? So you want to pull RS to 1 in order to write data to it. We just talked about this previously, just over here. Remember, RS pin is either picking up instruction or instruction register or data register. Okay, so there are 2 different registers in the LCD module. There's an integrated circuit chip on it. So there's one for instruction, one for data. Okay, very simple. It doesn't have different addresses for all different registers. There's just one IR instruction register, one data register, and in order to write into the data register, I have to pull this up to 1. So it doesn't show 1 or 0, but 0 for instruction, 1 for data. Okay, and it requires a enable pin to be put down, so it have to be up first and then being put down to enable the write. So start writing. So that's the only thing you need to be aware of. So that's the only critical thing you need to know. So I'm going to show you the details of the code on Thursday and give you probably the template to let you look at and print it out and give it to you. But the thing is, keep in mind, you need to put the enable pin down to ground from logic 1 in order to start writing. Don't have to worry about all the details here, since our example is really simple. So just put it down. Enable pin, just put it down to enable writing, so it's going to start writing. Okay, so that is for question 7. And there are a couple of other details, but I mean this lab is pretty simple. All the 3 sections are pretty much doing the same things, repeating, just changing the characters. So so the challenging part is wiring up the 3 different modules, the IPGA, the power modules, and the display. Okay, but other than that, it should be really straightforward. So we'll cover more about the timing diagram on Thursday. Let me see. What else on Thursday? Let me see. right, and also introduce the soft core, the microcontroller version of it as well, SoC. Okay, a lot of things to cover on Thursday, but I don't think we can finish the soft core, so we need another session on Tuesday next week as well to cover the Pico Blaze core. So probably won't be able to do the sequential circuit design on Thursday next week. I have to give the time to you guys. And then the spring break.
Yeah.
It's a good part. All right, so fast, right?
Yeah, just-
Any question? Yeah. Any question on anything?